Hello and welcome back. In section 3.5, we get to work with inequalities with integers. So first we'll go over the two types of notation that we will commonly be using for this set notation and number line. So we'll start with an inequality x is less than or equal to positive 2. So the set notation, x's that are less than or equal to 2, so that means 2 is the largest number in the set. One is an integer and also less than or equal to 2. 0 is an integer also less than or equal to 2. Negative 1 is an integer less than or equal to 2. And we could go forever to the left. The other way that we would commonly see this would be by sketching a quick graph on a number line. So with a little bit of imagination, we'll pretend that those are all exactly evenly spaced. And near the middle, I'll put my 2. So here's 3, 4, 5, 6, etc. that way. And 1, 0, negative 1, negative 2, negative 3 this way. And we want to just show the reader which places on the number line meet with this descriptor. So again, 2 is less than or equal to 2, so we put a dot on that. 1 is less than or equal to 2, we put a dot on that. I don't shade the stuff in between because we're working again with integers. So we use 0, negative 1 is true statement, negative 3, when x is replaced with that, we get a true statement. And to tell the reader that we keep continuing in this pattern, but only on the integers, up and to the left, we put an ellipsis. If we're going to the right, it would be up and to the right. Okay, pardon me. So the next one that we'll look at is 5 is strictly less than x. This time we'll just make a quick sketch first, and then we'll draw the set when we're done with that. So here's our 5 in the middle, and we'll just go a few in each direction. This time, the number that we got in our inequality statement does not actually work in the original. If I try to plug in 5, I'm claiming that 5 is smaller than 5. That is false. So I cannot actually use the 5. Trying out some other numbers, so 5 is kind of our border in between the two. Trying something from over here, 5 is less than 4 is false. Trying out something from over here, 5 is less than 6, that's true, so I'll keep the 6. 5 is less than 7, that's true, I'll keep that. 5 is less than 8, I'll keep that, and we go forever to the right. So we tell the reader that with our ellipsis. So then our set notation, we would start at 6. So we keep the 6, the 7, the 8, the 9, and we go forever, this time in the positive direction instead of the negative direction. So next, I want to introduce one of the properties of inequality. So what we're going to do is we're going to pick some random numbers. Let's see, we're at 457. So 4 and 57 into the video. So if my integers were 4 and 57, I could use a less than or equal to. Of course, a not equal to, but we're dealing only with inequalities. Now we're going to add something to both sides. So let's see, we'll do a 7. So 4 plus 7, 57 plus 7, so we get an 11, and we get a 64. Inequality symbol would still be a less than, how these are related. Next, we'll subtract a 3. So I'm just kind of randomly picking out some of the numbers from the counter on the camera here. So we have an 8 and we have a 61. Still a less than statement. If I take 8 and I add a -7 to both sides, adding a -7 is really the same as subtracting 7, so we get a 1. And we also have a 54. Still a less than statement. And let's see, we'll do one more of these and then we'll go for sort of a pattern. So we'll build off of the 1 and 54. This time we'll subtract -2. So subtracting a -2 is really adding 2. So now we're looking at a 3 here and a 56 here. Still a less than symbol. So the entire time we were working with those, the inequality symbol never changed. That is the addition property of inequality. If A is less than B, then A plus or minus C is less than B plus or minus C. So I can add or subtract anything I want from both sides as long as it's the same thing on both sides and preserve the direction of the inequality. I wrote it for a less than. The same property would hold if we switch this and this to a greater than. So for example, if we want to solve x minus 8 is strictly greater than 4, we would just add 8 to both sides of the inequality. So x is strictly greater than 12. Now as far as sketching the graph, we'll put our 12 in the middle and go 3 or 4 units on either side. So my first question is, can I keep the 12? No, we can't keep the 12. 12 is not greater than itself. So then I'm sort of mentally chopping this in half and seeing which side works. So testing out an 11 from here, 11 greater than 12 is false. 13 greater than 12 is true. I want the right side. And remember, we're on an integer domain, so I'll keep 13, 14, 15, 16, and forever to the right. So if they want a graph, there's the graph. If they want set notation, usually I'll ask you for both. 13, 14, 15, 16, and forever to the right. Let's see, so let's do a 5 and 9/10 is strictly greater than x plus 11. So I want the x by itself. If this were an equation, I'd subtract 11 on both sides. That's exactly what I'll do here. And I know that the inequality stays pointing in the same direction because of our addition property of inequality. I can add the same thing to both sides and preserve the direction of the inequality. So off to the side here, 11.0 minus 5 9/10. So there's 1/10. 10 minus 5 is 5, so 5 1/10. And the bigger was the negative, so negative 5 1/10. Tenth is strictly greater than x. So again, I like to kind of sketch it out. I usually will draw the number line first and then do the set notation after that. So this time I'm just going to pick an integer that's close to this. Remember, we're working in integer domain problems. So here's a negative 5, so negative 4, negative 3, negative 2, negative 1, and then we would hit the 0, and then the positives, remember, are over here to the right. So negative 6, negative 7, negative 8, negative 9, forever that way. So negative 5 1/10 is right about here, kind of in between the negative 6 and the negative 5. So negative 5 1/10 is greater than negative 9. That is a true statement. So I want this side. And we'll go forever to the left side this time. Now, there's two reasons I'm not going to include the negative 5 1/10. One is we have strict inequality. Two, though, even if we had negative 5 1/10 is greater than or equal to x, we would not be able to use the negative 5 1/10. Think about why. Why is that? Again, the issue comes down to domain. Negative 5 1/10 is not in the set of integers. If we're working integer domain problems, we still wouldn't get to keep that guy. So our solution set, we're approaching from the negative infinity side, and then we have negative 9, negative 8, negative 7, negative 6, and that's it. All right, so next we're going to kind of go through and again use some random numbers. During non-pandemic times, I have the students kind of pick the numbers for this, so I'll be drawing them kind of at random from numbers I'm seeing on the little clock on the camera here. So we'll do a 13 and a 26. Okay, those will work well together. So this one is a less than or equal to relationship. Let's see, we'll start by multiplying both sides by 2. And we got a 26 and a 52. Still a less than or equal to. I could have used a strict less than. I just happened to pick less than or equal to this time. So we multiply both sides by a positive. We stayed the same. Let's see, next we'll multiply both sides by 1/13. So for that, we would get a 2 and a 4, still a less than or equal to. So multiplying by a reciprocal is equivalent to dividing. So we've multiplied by a positive, we divided by a positive, no problem. Next, we'll multiply by a negative. So let's do 2 times negative 8 and 4 times negative 8. So I got a negative 16 and a negative 32. think about what happens to our inequality symbol. If you put a dollar sign in front of that, you're better off 16 bucks in the hole than $32 in the hole. Negative 16 is greater than negative 32. We'll keep the or equal just because I happen to pick it this time. Let's see, now we'll divide both sides by negative 4, so equivalently multiplying both sides by negative 1/4. Negative times a negative is a positive, 16/4 is 4, negative by a negative is a positive, 32/4 is 8. And we flipped again. So it looks like multiplying by a positive did nothing to our inequality symbol. Multiplying by a negative on both sides, dividing by a negative on both sides, flipped the inequality symbol. So let's write that up. So multiplication property of inequality. If A is greater than B, and case number 1, C is less than 0, then AC and BC, comparing them, if I've multiplied both sides by something, remember, less than 0, negative. We've hit both sides with a negative. The inequality symbol must flip. However, if A is greater than B and C is greater than 0, in other words, positive, the inequality symbol would remain. AC would be bigger than BC. So add and subtract all you want. Doesn't matter. Keep your inequality symbol exactly where it was. Multiply or divide, you have to know, is it by a positive or a negative? We don't cover the trivial case of multiplying both sides by 0, because then that leaves us with the trivial statement of 0 equals 0. Doesn't really help us in inequality territory. All right, so let's try out 5 is less than or equal to x 11ths. So if this were an equation and I wanted to solve it, I'd multiply both sides by 11. That's exactly what I'll do here. So 11 11ths is 1. 1 times x is x. So 55 is less than or equal to x. We'll draw the sketch and we'll test those out. So it's 55 in the hot seat. We have our or equals, and that is a true statement. 55 over 11 is 5. 5 is less than or equal to 5 is true. So I am going to keep our little number on the border there. And then it's just a question of, do I want to go to the left or to the right from that? If I try out the 54, 55 is less than or equal to 54 is false. So this side has to work. 55 less than or equal to 56 is true. So we will go this way with it. So then our set 55, 56, 57, 58, and our ellipsis saying we approach infinity. Okay, next we'll try out negative 5x is strictly greater than 35. So this one, I would multiply both sides by negative 1/5. And that's where alarm bells start clanging in your head. You're multiplying both sides of an inequality by a negative value. You have to turn the inequality symbol around. So x is now strictly less than -7. So again, I just draw my quick little sketch of the number line. -7 I'll put in the middle, and 3, 4 numbers on either side. So -6, -5, -4, -3. Just kind of watch, make sure you're going in the right direction on the negatives. I do tend to see folks getting them kind of mixed up when you're on the left side of the number line. So this time I don't get to keep my border. -7 is not less than itself. So let's try and see what works. So -8 is less than -7 is true. So this is the side that we want. So as far as our solution set, we're coming from -infinity. We had the -11, -10, -9, which I'll write as -9 this time, -8, and we don't get to include the -7 because of the strict inequality. So this next one, we combine kind of two properties. So -5 by the quantity x plus 2 is less than or equal to 3x plus 2. So in this one, before I start trying to solve this, I need to simplify first. So we'll use the distributive property. So -5x minus 10. We'll come back to that sign inequality symbol in the middle in a second. And the question here is, should we spin that inequality symbol around? In this case, no. I did not multiply both sides by a -5. All we did was simplify here. We didn't do something to both sides, so this was not a property of inequality. So we don't budge that inequality symbol. After that, we solve it the same way we ordinarily would. So we can either move the 5x or the 3x. Usually I survey the class and ask them which one they want to do. Or virtual, so I'll just pick, I'll move the 3x. So -5x minus 3x minus 10. Even though I don't know what 3x is worth, I know that that inequality symbol will stay parked. Remember, we can add or subtract anything that we want on both sides of an inequality, and the symbol won't budge. So -8x minus 10 is less than or equal to +2. Now I'll add 10 to both sides. So -8x is less than or equal to 12. So then I'll multiply both sides by a -1/8. And then clang, 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 there goes those alarm bells in your mind. We multiply both sides by a negative value. We have to spin the inequality symbol around. We had a less than or equal to, so now we have a greater than or equal to. So x is greater than or equal to -12/8, which is a -3/2. So x is greater than or equal to -1 1/2. So we definitely won't get to keep the endpoint. That's okay. So we're between a -2 and a -1. So there's our 0, 1, and 2 that way, our -3, -4, -5 this way. So -1 1/2 is right around here. So we just see which side we land on. So if I try out the 2, 2 is greater than or equal to a negative, that's true. So we want the right side. So then what we keep, -1, 0, 1, 2, and forever in the positive direction. So all of those will give true statements when plugged into the original inequality. Anything on that list, positive 10 trillion, plug it into both, true statement. So next we look at and or problems. We'll start with an and problem. So this takes us back to chapter 1. When we have an and, recall that this means we have an intersection. Or tells us that we have a union. To keep something that's in an intersection, remember it must be in both. Union, one or other, or both. We keep it. So we'll look at x is greater than or equal to -2, and x is strictly less than 5. So on this one, I'm going to sketch 3 number lines. So I want both of these numbers to be included on those number lines. So I'll try -4, -3, -2, -1, 0, 1, 2, 3, 4, 5, 6, and 7. Okay, and I'll make that the scale for all 3 of these guys. Okay, so I'll put my 0 on there, and we'll assume same scale for all 3. So on the first one, we're going to draw out the x is greater than or equal to a -2. So here's our -2. Pick a guinea pig from one side, see if it works. -4 greater than or equal to -2 does not work, but a +2 greater than or equal to -2 sure does work. And we do get to keep -2 itself. So I'll go ahead and sketch that. X is strictly less than +5, so here's our +5. Here's our -2, just for reference. And again, just pick a guinea pig on either side and see if it works. 0 is less than 5 is true, so I want this side. I don't get to use the 5 itself because we had strict inequality. So that was for x is strictly less than 5. And then we're doing the intersection. So for a point to be included on my final graph, it has to be in both sets. So all the stuff back here didn't work for the first one, so I don't get to keep it in the intersection. But -2 itself was shaded both times. That'll go in my solution set. -1 was shaded both times, 0 was shaded both times, and so on until we get to the 4. After that, it worked for set A, it didn't work for set B. I don't get to keep it in the intersection. So I'd keep -2, -1, 0, 1, ... But since it doesn't go on forever, I show that it ends at 4 by putting the 4 on the end after the ellipsis. All right. So next we'll look at one where we actually have to do a little bit of work to calculate this. Let's see, we'll try 6x is strictly greater than 30. And what did I pick here? 4x is less than or equal to 8. So if you have to solve two of them, solve two of them. First one, I'd multiply both sides by a positive 1/6. Multiplying by a positive, keep it as it was. So x is strictly greater than positive 5. Next one, we multiply both sides by a quarter. Again, it was still a positive, so we keep the inequality where it was. So x is greater than 5, and this one was an and, so an intersection. So these compound inequalities, that's what these are called, by the way, compound inequalities. I usually will draw the 3 number lines. All right, so we need 2 and 5 to be able to be on here together. So maybe put the 5 here, 4, 3, and 2, 1, 0, and a 6 here. Okay, so that's the scale for all 3 of them. So our first one, I'm going to sketch x is strictly greater than 5. So that would be the 6, a 7, an 8, and so on. Next up, we'll sketch the x is less than or equal to positive 2. So here's the positive 2. For reference, here is our positive 6. If I try out the 0, 0 is less than or equal to 2 is true. So I want the side with the 0. Oh, I messed up on my labeling there. 0, and this guy is a -1. All right. Do I get to use the 2? Sure do. 2 is less than or equal to itself. So this one gets an ellipsis going this way. So in my intersection, I want only things that were on both graphs. You might see a problem there. They had no overlap whatsoever. So this one would be an empty set. They had nothing in common. If a number is bigger than 5, it's not smaller than 2, and vice versa. Now, if I had that same problem, but I changed one word, I changed that and over to an or. So let's say we went through all that work. First 2 lines look the same. Really miss being able to have just nice computer generated number lines on my smartboard in person. Okay, so assume that we had the same problem, only we had an or in between. So instead of ending on x is greater than 5 and x is less than or equal to 2, now we have or. If it's an or problem, if it's in one or the other or both, we get to keep it. Let's see, any other big gaps. So let's put 5, I don't know, right about there. So 4, 3, 2, 1, 0. All right, so that should be sufficient. So I'll sketch the x is strictly greater than 5. So that is the 6, the 7, the 8, and so on in this direction. I'll sketch the x less than or equal to 2. So there's the 2, the 1, the 0, and forever that direction. We talked about how we figured those out before. But this time I'm going for a union, an or. So if it's in one or the other or both, I'll get to keep it in my final answer. So that means because of graph number 2, I get to keep all this stuff back here. So here's our 3, 4, 5, and here's our 6, 7, and so on. So because of the first graph, I get to keep the 6, I get to keep the 7, and all the stuff over in this direction. So now you'll notice that we have sort of a gap in this. I'll do a union then, just like we had in the problem. So ... 0, 1, and 2. Union, yes, you do need that symbol, don't forget it. And then we pick up at 6. So 6, 7, 8, 9, and forever that way. So it is possible for there to be a gap in here. Now, one other possibility that I want to account for before we move on to one other type of inequality that we're likely to see. Special case with the ors. So let's say we had x minus 5 is strictly greater than negative 2, or 2x minus 7 is strictly less than 9. So go ahead and pause it, solve those inequalities, and then we'll graph them together. Welcome back. So your first one, you added 5 to both sides. Add or subtract all you want on an inequality. The inequality stays pointed where it was. So same deal on this guy. We'll start by adding 7 to both sides. So 2x is less than 16, and we'll multiply both sides by a positive 1/2, so the inequality symbol stayed where it was. All right, so I'll go ahead and sketch my graph. We'll go ahead and pretend that those are evenly spaced. Here, we'll have one to the missing one there. All right, so 1, 2, 3, 4, 5, 6. All right, so we'll just go 1 through 9 there. All right, so x is strictly greater than 3. So here's my sort of dividing line. 1 greater than 3 doesn't work, but 8 greater than 3 does work, so I want the right-hand side. I don't get to use 3 itself. Then I'll sketch x is strictly less than 8. So here's my 8. Here's 9 on this side, 7 on this side. 7 less than 8 is true. 9 less than 8 is not. Go towards the true side. We don't get to keep the 8 because of the strict inequality. We didn't have the or equals part. Now I'm going to do the union, things that are in one or the other or both. Because of the blue graph, I get to keep all this stuff back here. Blue and red say I get to keep the 3. Blue and red agree on the 4, 5, 6, 7 as well. Because of the red graph, I get to keep the 8, even though the blue graph didn't keep it. Union, if it's in one or the other or both, I get to keep it. So because 9 is in red, I'll get to keep that too, and I'll get to keep going to the right forever. So this time our solution set is I, the set of integers. We keep it all. So with ands, it's possible to come up with an empty set. With ors, it's possible to come up with every single integer in the system. Okay, so that should give you enough. Oh, one more problem, my apologies. The compound inequality where we have one thing in the middle. This one, I'll just start its own page here. So these are connected with an and. Now, if we have one value that's less than an expression and then that same expression compared to another value, and we have the expression being bigger than one, smaller than the other, typically then this is merged into one 3-part inequality where we just put the thing they have in common in the middle. So if I were solving this one, I would put a -4 on both sides, so that's exactly how I'll start. If I were looking at this inequality, I would subtract 4 on both sides. That's exactly how we'll continue this. So instead of doing it to 2 sides, I just do it to 3 sides. Otherwise, no different than anything else we've done. So -2 is less than x is less than +1. Now the nice thing about this is when it's sandwiched in the middle like this, we don't need 3 parts of the graph. One graph is sufficient. We know we want the stuff in the middle. So here's our maybe 3, 2, 1, 0, -1, -2, -3, -4. That's far enough. We only want the stuff in between. So I don't get to use the -2, but I'll use the -1. That's in between the two. 0 is in between the two. 1 is not in between the two. So this time I only get to keep 2 values. So that should give you sufficient practice to work with section 3.5. So try out your 3.5 exercises. Remember to really practice with the ands and or, the unions and intersections. Review chapter 1, union, intersection if needed. If you have any questions, please let me know. Otherwise, I'll see you next time. Stay safe out there.